Hello and welcome to mathematical modeling. So mathematical modeling is kind of the driving force behind all of differential equations. So we're going to jump straight into what mathematical modeling is. So the general idea, a mathematical model is an equation that models the relationship between variables in a real life situation. And where differential equations come in are many mathematical models actually involve rates of change. So many mathematical models involve rates of change. More formally known as derivatives. And so these mathematical models involving derivatives are differential equations. So these mathematical models with derivatives are differential equations. So we're going to look at just a very basic mathematical model, or a few very basic mathematical models here. And in the next video, we'll see some more from other sort of regions of science. So this first one, we're going to look at population models. So when it comes to populations, we kind of look at, assume that individuals in a population are kind of reproducing at a similar rate, or we look at the average rate of change. So what we're going to do is we're going to set A of P to be essentially the rate of population increase or decrease. So it's the rate of population change per unit of time per individual. So again, we're kind of assuming that we're looking at essentially the average change in population per individual. So we might say that on average, rabbits produce, I don't know, 3 rabbits per year, right? Adult rabbits produce 3 rabbits per year, or just in general, the rabbit population, if you take the average across all rabbits, babies and adults, maybe they produce 2 a year, right? And so here, where P is the population size. then what we would get then is, since this is the rate of change, population change per individual, then the overall change in population, P prime, should be this A of P times the number of individuals, or times the population size. So this is the rate of change per individual times the number of individuals. Right? And this is simply the rate of population change overall. So this is the rate with respect to time. Right? Now, this could have all sorts of functions because I haven't specified what that A of P is. So the most basic model is called the Malthusian model. And the Malthusian model is just P prime is equal to a constant A times P. So here A is a constant. And it turns out in this case then, the P of T, oh, my screen froze, 1 moment. It turns out in this case that the population in terms of T, or can be expressed as some constant C times e to the AT. And here C is essentially the initial population size. So this is sort of the most basic model. And typically here, A is essentially birth rate minus death rate. So as you can see with an exponential solution, if the birth rate is higher than the death rate, the population grows. And if the birth rate is less than the death rate, then the population will shrink, which makes sense. Right? So note, if birth rate is greater than the death rate, then we have exponential growth. And if the birth rate is less than the death rate, then we have exponential decay. So this is all interesting, but in reality, most populations of some species have a limit based off of the environment they live in terms of how many of the species can survive, how large the population can get. So our next model is what is called the Verhulst model. I'm just going to see how things. So our next model is called the Verhulst model. And the Verhulst model essentially accounts for limited resources. So this accounts for limited resources. So at some point, the population will not be able to grow just because there's not enough food, there's not enough water, etc. At some point, the population will not be able to grow further. Due to too little food, too little water, too little space, etc. Right? And so the Verhulst model tries to account for this. So what the Verhulst model is we have P prime is equal to AP times 1 minus alpha P. And you will often instead see this as AP times 1 minus P over M. So again, here A and M are constants. And basically what we have is for P small, right, assuming alpha equals 1 over M is also small. Then our model essentially looks like the Malthusian model. Right? So the model looks like the Malthusian model with exponential growth. Right? But as the population gets larger, then essentially what's multiplying P is going to be getting smaller and smaller. Right? So as P gets larger, our A of P, which multiplies P, A times 1 minus alpha P, is going to get smaller and smaller and smaller. So the rate of change per individual is shrinking. And this winds up actually having what is called being a logistic model. So I'm not here going to solve this. We will learn how to solve it in chapter 2. But what I will do is just kind of show what will happen. So if here's our time versus our population size, if we mark where 1 over alpha or M is, what will happen is if a population starts small, it will grow sort of exponentially to start, and then it will level off and never pass. And so we could do this with a variety of solutions. If we start with more, again, it'll grow and then kind of level off. And then if we start above this limit, it'll actually turn out that solutions will drop down to that limit. So again, we'll solve this in chapter 2, and you can see kind of how these solutions form. We will also see later on in chapter 1 what are called direction fields, and we can kind of see these shapes form without actually solving the solutions. But these are our 2 sort of most basic population models. There are certainly more complicated ones we can look at. There are ones where you have 2 different species competing with each other. There are ones where you have a minimum size of population required for the population to survive, as well as that sort of maximum. But we'll leave it at these 2. And in the next videos, we'll look at various different mathematical models aside from population models.